Welcome, everyone, to the Ontology Summit 2025 on conceptualization, analysis, and formalization. Today is February 26, 2025, and this is the first session of the second track on theoretical knowledge and reality. We have an impressive lineup of speakers in this track, beginning today with John Sowa and Arun Majumdar, who will be speaking on, as you see there, Generating Ontologies. John is a well-known member of our community and member of the Ontology Board of Trustees. John spent most of his professional career at IBM, starting in 1962 at IBM's Applied Mathematics Group. Over the decades, he has researched and developed emerging fields of computer science, from compilers, programming languages, and system architecture to artificial intelligence and knowledge representation. In the 1990s, John was associated with the IBM Educational Center in New York. Over the years, he has taught courses at the IBM Systems Research Institute, Binghamton University, Stanford University, the Linguistic Society of America, and the Université de Quebec, Montreal. He is a fellow of the Association for the Advancement of Artificial Intelligence, AAAI. John and Arun have been working together for decades now, and their company, which they co-founded, is Permion, and it is now quite successful. It's got a number of customers, and it looks like the role of ontologies in these areas is going to be advancing as a result of his work. So now I would like to hand it over to John, who perhaps will tell us more about this. John.
Okay, on the first slide is a summary of the as the abstract, and there's three parts. So I'll be talking about a little bit about large language models, and they have proved to be very important for new applications of generative AI. But as a second point is that the approach is limited to certain kinds of applications, and it does not it's based on finding useful data in a vast repository, produce a kind of abduction or educated guessing. And that's a very serious problem, because when it's guessing, you have to determine what is the accuracy of the guessing. And that's where a lot of systems, generative AI systems, are hybrids that combine some method for detecting errors and avoiding them. Now, for our company, as Ken has mentioned, we do an integrated combination of the best generative methods and symbolic methods. And in the second part of this talk, Arun will go into considerable detail and also talk about how DeepSeek is also doing certain kinds of hybrids, but a different sort of hybrids from what we're doing. So right now, on the next slide, I'll get started. Now, talking about multiple ontologies, there's a lack of consensus on this next slide. There's a lack of consensus because different applications, different domains, and different requirements have very different ontologies. And there's also trillions of dollars of legacy software that does not have an explicit ontology. And the problem with the standardizing on an ontology it's always lags behind the latest developments. So and there are two kinds of ontologies: a descriptive ontology, which is always a work in progress. It describes concepts of empirical sciences, everyday life, and it may change with every new discovery or innovation. So a descriptive ontology that describes the world is never, ever going to be complete, and it's never, ever going to be absolutely accurate for everything. Now, a normative ontology for a specific application or a specific system can be a standard for a company or even an industry. And that's where you get specific conventions that are for which the standard is absolutely essential, and you have to have everybody agreeing to the standard. Now, the problem is, how can any AI system deal with this complexity, and especially these new LLM systems? How can they deal with it? Can they solve them? What? Now, that's what we're going to be talking about. Now, in the next slide is a diagram of a policeman who is answering a question. And then on the right side is the person who asked the question. And you can see that he starts at the beginning of the thing on the left-hand side, but then all he has in his mind is a jumble of all of the pieces that the policeman was talking about. And that's typical of any kind of conversation, that a linear language or notation is not really ideal for conveying complex patterns. And so we do need various kinds of treatment of spatial patterns. And fortunately, the LLMs can also deal with uh, diagrams of various kinds, and they can also do translations back and forth. But again, there's the problem of keeping them accurate. That's the issue of the next slide, where we um, talk about the patterns, so that there's first the patterns of everything that anybody knows. There's patterns of uh, physical, abstract, discrete, continuum, parts of things, shapes of things, spaces, three-dimensional spaces, four-dimensional space-time, and every theory of physics has a different ontology for a different system. And then there are dynamic structures for interoperating parts. And then there's life, in which you have every kind of organism and every living thing and all the things that exist and we have to deal with: behavior, society, ecology. And the notations that we're dealing with can mix an ontology with the logic. And you have temporal logics, higher order logics, procedural languages, diagrams. And how do you deal with this vast complexity? That's where we get to the next slide. And the and just as a summary, this shows 18 theories of language and thought, and starting at the top with Noam Chomsky and his generative syntax. And he claimed that that the generative syntax is the essence of language. Roman Jakobson, a major linguist of the earlier generation, and I believe a far more important linguist than Chomsky, in fact, and he talked about the problem that syntax alone without semantics is meaningless. Then you have a large number of other linguists and people working with computer systems and so on, and there's a large list of them. All of them, I summarized each one of them with just one sentence, but this is their lifetime's work, that you can't, one sentence is not really enough. But I'll mention at the bottom, there's Geoffrey Hinton was the key to doing the neural networks. Marvin Minsky made the point that the society of mind has many keys. It's not just one. There's a huge number of different ways of approaching what the mind does. Now, my favorite philosopher, Charles Sanders Peirce, made the point that the mind is the totality of a lifetime of signs. And Zelig Harris, who was Chomsky's thesis advisor, I think is closer to the actual nature of language. He made the point that empathy is key to understanding what the speaker means, that we use empathy constantly in understanding other people, and that is the main issue we have to deal with. The next slide talks about a title. The next slide is "I don't believe in word senses," and that's the quotation by the lexicographer Sue Atkins, who worked on dictionaries and defining dictionaries and developing dictionaries and word definitions for her entire career. And Adam Kilgariff is another uh, lexicologist, and another man who's been also dealing with various languages and with dictionaries, and he had collaborated with Atkins on much of the work. And he said that a task independent set of word sentences is not a coherent concept. You cannot have a fixed set of concepts for any particular task. There's just constantly change. There's no reason to expect the same set of senses to be relevant for different tasks. And the set of senses defined in a dictionary may or may not match the set that is relevant for any particular natural language processing. And professional lexicographers understand these issues very well, and generally they understand those issues better than most people who are working in computational linguistics, in fact. And the senses that they select for a dictionary entry are based on editorial policy of the dictionary company, and also about assumptions about the reader's expectations, and they may not be accurate for any particular application. And there's a link if you want to go and read this in more detail, because Kilgariff and Atkins had done a lot of work, and it's very important to understand what they mean. And then the next slide, we have a discussion of the discrete and continuous issues. The world is a continuum, but words are discrete. How can you have discrete words describing a continuous world? And the answer is you allow continuous variation in the meaning. And why are words discrete? And the fact is, it's much easier to construct things out of a set of discrete things than out of a continuum. So that's why all of our languages have a set of discrete units. And the next slide talks about the dynamics of language and reasoning, that natural languages adapt to the ever-changing phenomena of the world, the progress in science and social interactions in life. And no computer system is as flexible as a human being in learning and responding to the effect dynamic aspects of language. And that includes the latest and greatest LLMs. They are still far less flexible than the average human being in using language. So in the strategies for language processing, there's the neat methods which use formal grammars with model theoretic semantics. Now that's very useful for very precise topics. But there's also the scruffy methods for dealing with practical applications and everyday conversations. And what we're using with and for our Permion company, we have a mixed approach that can use a mixture of the neat, precise methods and combined with the scruffy, everyday methods that people actually use. So that's the issues that we have to deal with. Now, we also have to do the next, we relate models to the world. So there's the world in all its huge complexity. And in the middle, we have a graph structure of some sort, a network model, which is an approximation to the world, which may be good, fair, poor. And then we have on the right a theory. A precise theory can be an actual have that model as its precise denotation, and the theory can be either true or false of that. Now, the engineers have a saying that all models are wrong, but some are useful. However, the world is continuous, disordered, and fuzzy, and there's always that discrepancy between the two. Now, natural languages are flexible. They can adapt to anything, and that's the question. Combining precision and flexibility is a challenge for any of our systems. Now, the next slide shows a diagram. At the center, there's language and a kind of star base in the middle. Now, language can relate our ontology to a symbolic model. This is a symbolic model represented as a graph of some kind. And then there's the mental model, and there's a little picture of what we might have in our mind of a cat on a mat. And then there's the symbolic model that has the words linked together. We can have an ontology that deals with the subject matter. We can have reasoning. We can have action upon the world. And there's the mental model that is derived from the world and the action upon the world. But language is the middle, can relate all of them. And by language, I include all of the uh, versions of natural languages and special cases and all that. So the problem is, how do you deal with all of this? Now, the next slide, we're talking about how do you implement that hexagon. And the corners of the hexagon represent aspects of knowledge, and language represents conscious knowledge that can relate all of them. And our challenge is to design AI tools to support all of the above. So on the next slide shows a diagram of the logic of pragmatism by Charles Sanders Peirce. And standing in the middle, there's a picture of Peirce. And that shows the stages of deduction from cognitive memory. That can represent everything on the World Wide Web if you're using LLMs of some sort, but it could also represent whatever you have stored in your computer system locally, or it could represent what's in the head of some individual person. Now, by abduction, you extract guesses and adapt the pieces from the cognitive memory, which go into your theory, and then you build your theories and revise them to represent whatever you're talking about. That's a formal reasoning method. And then by planning, reasoning, and evaluating, you use deduction to come up with some kind of a prediction of what would happen from that theory. And then by action, you act and test and do whatever searching may be necessary. You do the action upon the world. And then by induction, by sensing and learning and perceiving and discovering, you create new information that goes back into cognitive memory. So there's that summary of the cycle of reasoning, of induction, of abduction, where you get your guessing. Now uh, that's where the LLMs are at their best. They do educated guesses, but the guesses can be wrong. They can be hallucinations. So that's why you need the deduction to determine to analyze and evaluate precisely, and then you get into the prediction and the action upon the world. So this is uh, the 4 stages. This is Peirce's 4 stages, and those are exact quotations from Peirce's writings. But he also distinguished a 4th, more informal kind, and that is, besides these 3 types, there's analogy. An analogy is a general principle that has aspects of induction, abduction, and deduction, all in the same uh, method. So that's an important thing. An analogy is very important, but we also need the first 3, the induction, deduction, and abduction. Now, John Boyd developed an OODA loop, which is a thing that he calls the OODA loop, which is representing the observe, orient, um, decide, and act. And this OODA loop is very similar to what Peirce's abduction, deduction, and induction. It's a very similar stages, and he labeled the stages differently, but they're very, very similar. And Peirce's theories that he developed in terms of formal logic can apply very well to Boyd's OODA loop, which was used. He designed that originally for he was originally in the war. He had been an airport, a fighter pilot, and he was teaching other pilots, and he developed this OODA loop for teaching pilots how to use it. But he later discovered, and the next slide, he later discovered how to use the OODA loop to handle he hmm, let's see, what's it, And the next slide shows an application of the OODA loop to wicked problems. Now, this is developed by two people, Graves and Garrett, used OODA loops for analyzing and solving what engineering problems, which they called wicked. And there's their exact quotation. Wicked problems involve complex interdependencies between the systems evolved and incomplete, inconsistent information about the problem context. Wicked problems are dynamic and span many domains with complex legal, ethical, and societal aspects. And basically, that's true of every large problem of any kind, of every large project, of design, anything from designing an airplane to designing bridges, designing highways, to designing a satellite, designing an entire system, a corporation of any kind. You always run into these complex problems, and you never have something where you can pull off a already predefined ontology. It's always dealing with relating everything. And the problem is that large language models, which are designed on previous data, even data coming from the entire internet. If you take the entire internet and process everything available on it, you still cannot discover the solutions to to truly wicked problems, because they wouldn't be wicked if somebody had already solved them. So a wicked problem, by definition, cannot be handled by LLMs, because LLMs can only discover stuff that's already been solved, and an unsolved problem can't be solved. Now, sometimes they can do some helpful things by bringing together pieces of other problems, but if it's really truly wicked, it has new innovations that are not already available. Now, the point that I want to make is that humans are not obsolete, and that this is something that some of the people who are working on AI and the generative AI, they think that, oh, we're so far advanced that we're surpassing humans, but that is not true. One thing that uh, Kant was Immanuel Kant was quoting Socrates, and one of the points that he said is that the Platonic or Socratic questions drag out of the other person's cognitions what lies between them, what lies within them, but one be, but and it brings out what one brings to the other, to what brings to consciousness of what he actually thought, so that the point that Kant was making is that the points that we have inside our head are not articulated in language. And the thing is that if we have LLMs that deal only with language, it misses a huge amount of information that we have in our heads that is not articulated in language. And Zelig Harris, who invented transformational grammar and was the thesis advisor of Chomsky, made the point that we understand what other people say through empathy, imagining ourselves to be in the situation they were in, including imaging something to imagining to say what they would wanted to say. And that is a fundamental thing, that when we understand people, we are using a huge amount of our feelings and our lifetime of experience to understand what they're saying. We are not using LLMs to just look at words. We're looking at everything in our lifetime. That gets to the final slide in my talk. And that's a question of whether these LLMs are a path to artificial general intelligence. And some people are claiming that, and I would say absolutely not. It's good, but it's not going to give you AGI. Now, Zelig Harris made the point that we understand other people, what other people say, through empathy. And George Burns responded to that. He didn't respond to it because he didn't even know that Harris had said it, but he made the point that sincerity is everything. Once you can fake that, you got it made. Now, he said that as a joke, but the point is, it's actually true. empathy and sincerity depend on feelings, and AI systems don't have feelings. But the question is, could they fake them? Could an AI system fake feelings? Now, hardcore programmers claim that feelings are irrelevant, but feelings are essential for all living beings. From bacteria on up, feelings are a protection against danger. They are a guide to food, health, better living conditions. And with other people, they promote cooperation and avoidance of conflict. They are the basis for ethics, aesthetics, ethics, and empathy. And the question is, are feelings necessary for artificial general intelligence? So that's the ending point that I would like to raise. And the next, I'll hand over to Aaron. So Aaron, if you want to take
Okay.
over.
Yep. Thank you, John. So we'll, start to look at how we apply all these different pieces, the abduction, deduction, induction, the theory revision, and inside of this, there is an OODA loop that is always happening because while part of it is the OODA loop for the machine, another part of it is OODA loop of the human. So if you look at this diagram, it's sort of labeled, and you'll sort of see that in our conception of this kind of worldview, we have someone here, a human being at number one, called a SME, a subject matter expert, an SME. And an SME, as you're building ontologies, you gather materials, you do a variety of things, and there's a calibration that kind of goes iteratively along. And that calibration, I use the word calibration and not the word tuning, because humans calibrate their understanding in a very different way than machines get tuned or fine-tuned with techniques or methods like relational learning and so forth. Really what's happening here is, I'll walk through this diagram. There's there's some kind of ability to do language parsing and to understand the dependencies within language. And the subject matter expert is also the source in this calibration of a seed ontology. In other words, the origin of meaning comes from humans. The origin of meaning doesn't come from machines, it comes from humans, because humans build machines to understand human meaning. And so there's a seed ontology that is requisite in this process of what is it that the machine serves. And the issue is that very often, as John said, you have the imprecision of language as well as its precision, because you have to be sufficiently vague to be able to talk about things in this continuous world, but precise enough to be able to start to formulate models. And so there's this natural ordering that comes out where the seed ontologies, the data inputs, the things that you put together have to be ranked and organized. In other words, there's a relationship between something that's more general versus something that's more specific. And that's sort of at step 5. And then there's another piece to this where there's a mapping to what does the machine see in terms of its worldview, right? So number 3, which is a natural language semantic dependency parser, and number 6, where it says a machine learned semantic dependency parser, they're actually different things, because one is from the perspective of the human and the other is from the perspective of the machine. And then you select for those things that allow you to curate and represent models by the mapping of structures into what we call proto-ontologies. That's number 9. In other words, a proto-ontology is not an ontology. It's something the human then redigests and works with. And that's why at the top, you'll see that search is number 10, because after you do this, you'll find gaps, you'll find things missing, and you want to iterate the process, and there's that OODA loop coming in, right? You want to come back, and then the human back in the loop with the machine. So that's sort of the system context. And if you sort of look at the seed ontology process, you would have to provide some structure. And I'm going to walk you through some examples here where you have to also provide some information set, some documents. And you're essentially telling the system, build a set of concepts and relationships, right? That's how data is interrelated. And that interrelationship, sort of ends up in this graphical structure, which you can represent in using linear algebra, for example, in matrix form, right? So there's lots of good technology out there to represent graphs as matrices. And then from that, it feeds downstream that proto-ontology process. Now, the steps in between that matrix and the graph and the pieces, well, that's got other pieces to it. So, for example, you start with raw text files. That's your document inputs. If you have garbage in, you'll get garbage out. So you need clean Unicode files, because human language comes in a variety of formats. And, the representation of Hindu glyphs versus Chinese glyphs versus Western glyphs or Cyrillic glyphs, they're all different codings, but they all have meaningful representations today in the Unicode standards. So you need to have clean Unicode, not just a jumble of randomized, bad data input. There are statistics that get measured. Why? Because you want to know the degree to which something that's being inputted is random, right? Or you want to at least measure the statistics so that you can understand things like the type token ratio to understand passages that have higher information content versus less information content. Very often when you digitize documents, there's always some corruption that occurs, broken characters, sequences that don't make sense. And so you want to understand entropy in these things. And then once you have some form of, let's call them chunks, right? These tokenized chunks, then what we do in our engine is we translate them into a Prolog text graph. And we do things like we build trigrams out of these statistics. We use embedders of various sorts that get trained on background. And we use inductive learning to start to create the ontology hierarchies. If you look at ontology induction, there's a couple of different ways of doing this. There are no correct methods that, sort of one size rules all. And so that's why you have these crisscrossing arrows, because a lot of this is also going to be steered by the human. And this is, again, where that word calibration comes in. So the human is not a passive component of the system. The human is active, right? The human has to say, hey, this is going in the wrong direction. The meaning is really this, or there's I need to add that. There's that search and replenishment of information to help guide the processes. But inside of this, there are statistical methods such as inverse information gain. So you can think of this as sort of a bottom-up and top-down iteration cycle to build both simple classifiers and complex non-monotonic classifiers. And what you're going to get out of this is a bunch of fragments, and you want to be able to organize these fragments so that you can connect them together. So in some cases, we build features based on Markov chains. There are lots and lots of different things. There are embedding measurements that can be used as well. So all we're really talking about here is we're building something in a logic programming language. And it's fairly mechanical, and the human can easily rebias the inputs. Here we're just doing a little bit of zoom in on what does the more complex side of it look like. So in the previous case, you get a very simple hierarchy, and I'll show you what that looks like with real world data. Whereas in this, you get a tree structure, what people normally see as sort of a taxonomy, right? And so you get these different fragments, and once you have these pieces, you can start to do merges, right? And composition based on how the common syntactic matchings of concepts occur. So if we look at a real world collection, I took a set of data around DeepSeek. Why? Because DeepSeek has achieved a lot of notoriety. And I thought, it'd be fun for us to take a look at DeepSeek through the eyes of the technology and the application of the methods I've just shown you. And so there's a bunch of documents here, maybe 15 or so documents, including the DeepSeek technical reports. There's a couple of different documents in here with different even variations of document iterations, in other words, document versions. So at the top, it's, a general one, which is attention is all you need. Well, that's not really from DeepSeek, but it's very germane because it's such a fundamental part of every autoregressive generative pre-trained AI. That means OpenAI, DeepSeek, any LLM, right? And then, there are discussions about DeepSeek. So that's challenges in ensuring AI safety in DeepSeek R1 models, the shortcomings of reinforcement learning strategies. And then there's a couple of them. So you'll see a Condor, a code discriminator integrating general semantics with code details. And then critical tokens matter. There are two of them here because one is a revised version of the other, right? So one is an original version, and then the second one is version 3, which is 3 revisions further. Now that's interesting because it also allows you to capture conceptual evolution, right? So the same document evolved a couple of times has value to understanding of building the ontology of the domain. So that's kind of what the document set is about. And when you process this, you actually get, I've zoomed in here, it actually looks like a rat's nest. You can't even see the white space on the screen. So this particular screenshot is to illustrate the feature of fragments. So there are some fragments here that you can see are dyads. There are some that are triads right at the bottom. There is a little curved triad. There are some that are trees. You can see this Y-shaped tree to the right-hand side in the middle of the screen to the right. And then there are those that have these much longer, kind of more condensed concepts that link to lots of things, right? So that's what gets produced. That's what the fragments are that we were talking about. And when you do hierarchy induction, this is literally the monotonic hierarchy induction output. So in this particular extraction from the texts, that collection of documents, this is a kind of entailment relationship, okay? And so you do have to have, again, the seed ontology to help you steer what embeddings and what these, I'll say, fragmentary components do. Otherwise, there's no rhyme or reason to the order. But let me read through this. It says DeepSeek version 3, and that little loop at the top says DeepSeek entails DeepSeek. Okay, that's pretty obvious. But then it goes on to say it entails this evaluation. That's a very strong link. And the evaluation entails performance, which entails training, which entails benchmarks, that entail models, that entail tokens, and there's something called strong and context. So these tokens have this entailment of strong to context to GPT-4o. Found that very interesting. That entails following DeepSeek version 3 base. So if you sort of take the end of this chain and you take the beginning of this chain, what you have actually is not something that's truly linear. It's a cycle, okay? And so you can see in this process that DeepSeek is actually a distiller of GPT-4o. And understanding that DeepSeek is that from the document collection is actually very difficult without a human being reading it all. But this automates that process so you can start to see what the hierarchy looks like along a line of entailments. It's kind of interesting. A more, a complex one is where you start to zoom in on that set of interrelationships and their graphs, right? Where you can see that there's various versions of DeepSeek, and there are these Math 500 and then math-related activities, and you're starting to get a sense of what this collection is built up of. This one's very interesting because when you navigate, you can see floating point 8-bit here, FP8, and you'll see the word cost-effective, use, and training, and low precision. So we've tried to have a kind of a gravity field effect around the semantic distances between things. So that's why low precision, even though it's not directly connected, is floating close to FP8. And you can see that there are these, general matrix multiplications are actually handled by this FP8 piece. And there is this ground truth at the top there, where it talks about ground truth and tokens means there's a symbolic thing here, and that you have this high quality kind of dependency. So there's a symbolic model embedded in what DeepSeek training looks like. It's very interesting. If you start to look at DeepSeek from the perspective of what are the inter-document relationships? How do they connect to them, right? You'll start to see that, for each document, there is an ontology, and between the documents, there's an intertheory about how these ontologies are connected. So now you're starting to get a sense of, okay, I could start to think of a top-level ontology. And there's always going to be noise. There's going to be contextual noise that a human is going to have to say, actually, that's the wrong term. Remember, I said the human is an active participant. So if you squint at the bottom right, you'll see the word we in there, right? And I wanted to leave that in because what you would do is you could actually click on these things and they'll pop you to where it is. And you could actually refine we to represent the group representing the we, which is the contextual resolution of that co-reference. And so there are things that are going to be ambiguous that a human is needed for, and there are things that is going to be precise enough that the machine can accelerate the human's understanding of this complicated domain. And, one of the things I did was I said, well, let's apply, now that we've collected all these pieces, let's do a fusion and merge output to look at the architecture map of how was DeepSeek assembled, okay? And it's fascinating because if I had to go through all the documents and say there's supervised fine-tuning, there's the pre-training with 14.8 trillion tokens. There's the reinforcement learning, the model evaluation. There's the multi-token prediction. And FP8 appears here, right, which is mixed precision training and multi-head latent attention. This is the sum of the techniques that DeepSeek is using that fundamentally results in its performance. So if I had to work this out by hand, reading all those documents, instead of having the system generate this based on a combination of analytic tools and human tools, generative pre-trained AI, okay, where we can make the guesses, but then we use the background as integrity constraints. That process takes what would normally take months of work and reduces it down to, a few hours. And then you're done. And now you can start to say, okay, if we were to, build, what techniques and how would we connect them? And now you can start thinking creatively about what you do with this knowledge. So this is what it takes to sort of have a basic understanding of a domain. It's a bottom-up and a top-down approach where the human is very much in the loop. The human is never out of the loop. And, coming back to John's point about Boyd, there's a human OODA loop. And on the technology side, there is a Peircean, a Charles Sanders Peirce cycle of pragmatism in using abductions, selecting the integrity constraints and pruning inconsistent, unsystematic, or contradictory pieces, executing theory revision, and then building deductions. And the human is always in that loop, doing the observe, orient, decide, and act. And of course, the human can say, you know what? There are too many gaps, holes. Let's get some more information, right? By searching external sources, the internet, and what have you. Part of that can be automated, but largely when you're talking about unknown unknowns, this is where human imagination, the ability to visualize and imagine and take the machine in directions that it could never get outside of itself. And that goes back to, if you think of Gödel's incompleteness theorem, no system is powerful enough, of course, to describe itself. So you need the interaction between the human and the machine, to feed the new information in. So that's really what I wanted to kind of show you, is a little bit of what do we present, what do we deliver. This is running right now. For those of you that are interested, there's the Amazon government cloud, the intelligence cloud marketplace, which is where the nation's most, I'll say, sensitive and critical work is done by people that need technologies that are not only probabilistic or statistical, but have I would say, explainability and transparency in being able to articulate models, and in which human expertise, human analysts can iterate and work in this very, very close partnership between the human and the machine. So thank you.
Thank you, Aaron and John. And now I will open up the meeting to questions. So let's look at the chat here.
I see Todd and Ravi has their hands up.
Pelican, Todd.
And
Okay. Who was
Okay.
first here? Todd?
Okay. Hi, Arun. Hi, John. A quick question, hopefully a quick answer. You both mentioned this notion of the use of a seed ontology. What is the
Yes.
extent of that ontology? And if you're using first order logic for it or prologue, is there a bound on the arity of the relations?
Well, I'll start with a brief comment. With the VivoMind, we had started with a large number of
I only heard about
sources.
10% of what you said because it was chopping in and out. Can someone repeat the question for me if they heard it?
Kenneth, did you hear the question I asked?
Yeah, you're You are dropping out.
Oh, okay, I'll repeat the question, Arun. I'm sorry
I-
about that. My question was about the seed ontology that you and John had referenced, and I wanted to know
Yeah, I only
what,
heard like 1 out of every 5 words, so I don't know what the question is.
am I coming across now, Kenneth?
So Todd is asking about your seed ontology and about the arity of your relations. Did you hear that?
I'm gonna see if my network is. Let me see network
Well, I
preferences here.
I
Maybe
can
it's my
answer.
network. I don't know.
I can start the answer. Aaron,
Uh,
Aaron, can you
Yeah,
hear?
John, go ahead.
I can hear you now.
Okay.
I'm just looking to see if I have a.
Well, I'll start with a brief answer to the question, and the point is that we had been developing ontologies for the past 20 years. Over 20 years when we started with VivoMind, and we used a variety of sources, both linguistic sources from various linguistic sites, as well as a variety of ontologies that I had developed for the books that I had been writing, and we put them together in a large collection that could be adapted to any particular application as required. That's a brief answer, and Aaron can continue.
You might have to
Um,
ask the question again for Aaron, now that you can hear.
Arun, did you hear John's response?
I guess maybe you can write your question. Yeah, I did, but it was fragmented. Let me see if I have. I'm gonna just unplug this. I've got a. I'm gonna try just. Let's see if I can redo my. I'm gonna try and switch to a different network. So just bear with me while I do that.
Well, John, if I could ask a follow-on question.
Sure.
I gather there was a collection of
let us
ontologies
see
that you
first
have,
if we
and then you
can
can join
hear
them
you.
together or select which ones you want to use for creating a seed ontology for particular use?
Well, over the years, we have been developing large numbers of very detailed ontologies for various applications, and the basic source consists of was built from a variety of different ontologies, a verb ontology that was designed for handling verbs. And also we have developed the language independent work so that we can start with a translation from any language and build on that. Well, there was one example was a need for for analyzing Chinese texts directly from China, and we had there was a woman who was a Chinese linguist who had been unemployed from her teaching jobs and was very happy to have an opportunity to do some work on ontology. And what she did was first write a grammar, a grammar for Chinese that was suitable for what we were doing in our representation. So she had a complete grammar for Chinese that we could use with the VivoMind. This was with the old VivoMind system, and it was an excellent source for analyzing Chinese documents and doing the same kind of analysis with Chinese documents that we were able to do with documents in English and a few other languages. And in fact, for one of the most difficult parts in Chinese is to recognize proper names because the And the words that are used in proper names for Chinese can be any characters available in the Chinese language. And that means that there's no distinction between a proper name and any other word in Chinese. And it's very difficult, even for the Chinese themselves, to scan through a document and select out all the names. But since we were doing a complete parsing and a complete analysis of the syntax of the entire document, it was much easier to determine which triplets. Chinese names usually have three parts. There's a family name, a generation name, and then a name for the particular individual. And so those three parts could be any characters in the language, but because we had done a complete syntax analysis of the entire text, it was very easy to determine which triplets happen to be proper names. And that's an example of the kind of thing that can be done.
So I'm back. Hopefully everyone can hear me now, and I can hear you all clearly.
Yes.
Okay, sounds good.
So I guess the question from Todd, yeah, so we build graphs. So the prologue predicates represent a graph structure. And so the question of arity is not the question of a predicate. It's the question of arity at a node in the graph, right? And so because we're representing a graph structure, our foundation, which is what you extract from that, that's when the arity becomes important. Now, obviously, arity is important when you're representing things like case role theme relationships for terms, right? That you're looking at the, Charles Fillmore's, what is the agent, what's the patient, what's the instrumentality, things like that. Of course, that's there. That's part of the background knowledge, right?
Well, yeah, the reason for my question was John's reference to the fact that knowledge really depends on these relations among things.
Yeah, absolutely.
Thank you.
And yeah, and we use rhetorical relations as well. We use rhetorical relations. We use the case role theme relations, which is sometimes called frame semantics. So these are all ontological elements. I don't know who's next.
Hello. Ken, you are muted. Ken, you are muted.
Sorry, I'm muted. Yeah, go ahead,
Yeah.
Robbie.
Okay, I have a couple of things on your first arc. I'm sorry for sore throat, so I'm not very clear. But on your first diagram that you showed, Arun, you have two things, the seed, and also there is a what I would call is training set, but you call it something else on the top left in your first slide.
Yeah, we distinguish training sets. Okay, so we distinguish and separate the concept of a training set from the concept of a calibration. A calibration is originating with the human being, right? The human being says, this is how I determine, define, and say something. So it is knowledge that normally would be implicit or tacit, and you're eliciting the human to put that information in. So it's not a training set, okay? It's human input, and then you have training sets, right?
I see. On top of that.
On top of that, yeah. It's a very good question and a very important distinction, because as John said, you can't use the lexicographer standard when you're talking about expertise in a domain, right? There is its own domain contextuality.
Yes, thank you. And similarly, when you were selecting a set of documents, you were also selective in text.
Yes.
Later in your slides.
Correct. Correct.
Last question from me. You know Indian languages, so I can say dhatu or the verb is the root of what you intend to arrive at as a meaning in the end. So why are these derived languages like English and so on do not have the same kind of grammar type structure to derive the meaning out of language documents, text documents?
So one of the points I made was about the importance of Unicode, and I mentioned, you have to encode languages like Hindi. If you're studying
Sanskrit.
ancient languages, well, you need to encode Sanskrit, right? So,
Yes.
all of the variety of languages and encodings is very large, and different languages may superficially have different structures, like subject verb object versus object verb subject, right, where it's reversed. But intrinsically, there is going to be the interpretation, which is what is understood by a listener of the language. That goes back to John's point about empathy, right, and understanding, which has to come from a cultural perspective. And so the origination is going to come from human beings, right? The machine is not going to get that without human beings codifying that to say, and I'll make a very, very grossly negligent black and white comparison. I can come into a conversation saying, the world is out to get me, okay? And so that will give me a certain view. Or I can come into a conversation saying, the world is out to help me. They're completely different, right? And we'll have different results. So that part has to come from the human. I see, I guess, Alice, is it Alican? Alican, yeah.
Yeah, so yeah, Alijan. Alijan is there.
Alijan, thank you.
Yeah, exactly. So yeah, thanks for the presentation. It was really important for me because I am also doing something similar, not like a basic form, so to speak, for my research. But what I distinguish is the data and the theory, where my theory is the ontology basically, and the data is what I gathered. And then through the abduction, I am filling up the ontology, and I am also updating it through the state machine. So it is like a basic form of it. My question is, how do you justify what you have found through the abduction so that you insert it to the ontology? Because the 3D, yeah.
is a great question, Alijan. So what I understood you said is there's the theory and the data. There's a piece missing there. And the missing piece in that dyad of theory and data is human, right? So the human has to be an active piece of this equation, because much of the tacit knowledge, okay, that a human has, this includes the human bias, right? So bias is not a bad thing. It's a good thing, because bias is what changes what makes a difference between, for example, a good banker from a bad banker, or a good trader from a bad trader, right? A bad trader will lose money all the time because their bias will cause them to lose all their investments, whereas a good, a stock trader will have biases that allow them to be successful. So bias is just another dimension in the equation. And so when you deal with expertise, particularly expert knowledge, it's not enough to have the data, and it's not enough to have the theory, because the theory is only going to be good enough for what the theory's original intent was, and the data is going to be missing the interpretation in the context, because that's what the human has. So what is, truth or reality has to be determined by the agreement or the consensus between human and machine. So the judgment, the question of judgment, is why the human is so important in this equation. you know, why am I interested in DeepSeek? I'm interested in DeepSeek because I want to understand very quickly. I don't want to spend 6 months reading all the documents, right? I want to read those parts of the documents based on where I am steered, where I need to look. So the machine is a tool, right? But if I don't participate in the tool, then the machine can give me all kinds of wrong direction, right? So I'm always saying, well, I selected this set of documents. Even the selection of documents, what I give the machine is a bias right there, right? And so I am participating in the judgment myself. So yeah, it's the human, the data, and the theory. And that's very much
like the
Go
cycle.
ahead.
Yeah. So the follow-up question. So that means that between the theory and the data, human is there to put the justification and follow up the
Correct.
cycle. So that it's great. All right, perfect. Thank you very much.
You're very welcome.
Without using your architecture as a tool, namely Permion architecture, you could not have deciphered the internal graph structure and details of DeepSeek.
No, it would have taken a long time.
Yeah, and then can you kindly think of another experiment that you use a similar to Permion type of some other architecture and play on DeepSeek and see the differences between what you find to
So
really understand DeepSeek?
yeah, so an interesting use, which is not illustrated, but you can take the architectural map, okay, the last diagram I shared, and it's the last slide. You can take that map and use it to hypothesize improvements, okay? So you can now bring in other knowledge and say, given this achievement as my fixed knowledge, I'm now going to say this is my ontological foundation for a systems architecture. Now for each piece, what is a more optimal implementation strategy? Or put another way, you are doing round trip engineering. You're going from literally from semantics to code. Okay, and that's a very exciting area. And we certainly do that internal to Permion. Now, you know, Permion is a company that focuses on maintaining a strategic technological advantage over all other competitors because of the customers we serve. And so how we use our tools to produce value, right? That's the consumption of the ontology, right? Now you're talking about, okay, how do you do code generation? So an application of this is to generate software, code, and modules. Okay, so that's a very powerful application. I won't go into detail, but you can imagine that this is the way you can advance a competitive advantage. So that's a great question, Ravi. Thank you.
Thank you for a great answer. Thank you.
Any other questions? Anyone else want to speak? There. Gary,
someone asked what tool you were using to create your assertions. Your was to convert textual papers to graphs in your presentation today.
Sure, that's a great question, Douglas. Thank you for asking. So Permion builds a compiler. It's called the X Machine Virtual Machine. It's based on theory of X machines, and it implements Prolog as its user programming language. The outer layer of that language is Logtalk, so we have an object layer, but X Machines is a reduced instruction set compiler for logic and functional and graph-oriented programming. And so when we actually build the structures, the structures are represented in the form of compressed, sparse matrices internal to the engine. And we compile very complex expressions that you can write in Prolog using a JIT compiler internally. So it does not use a Warren abstract machine. It's a completely different model of computation. If you're interested, you can look at Peter Wegner's book on interaction or interactive computation, and feel free to send me questions. I'll be happy to point people out. We will be, you know, and I don't know if it will be in 6 months or a year or it'll be in 3 months, but we will be, and we do have a full end-to-end developer kit with debuggers, code analyzers. It supports full multi-processing, multi-threading, co-routing, parallel and distributed computation. So yeah, it's a full platform, and anybody who knows how to program in Prolog will find this very easy to work with.
Yeah, I would like to add a comment, by the way. Prolog is extremely powerful, and any other language that anybody is using for AI or natural language processing is way inferior, and switch to Prolog and your power will jump up by orders of magnitude.
Yeah,
I started implementing large language model, did the implementation in Prolog. It's definitely the most powerful language.
Yeah, so we provide a full interface to Java, a full interface to Python, so it drops into Microsoft Visual Studio Code or any other IDE environment. We have all of those tools, and we're exploring whether or not we release our own foundational models, because that would entail having to release XVM as a runtime. So, so we're looking at that and looking at the possibility of community development.
By using the reduced instruction set, what are you compromising, Arun?
You're actually gaining, you're not compromising. So what happens when you use a reduced instruction set approach, you're able to take a program that you wrote in XVM and generate the VHDL and Verilog to create an ASIC or an FPGA. So you can't do that today with most of the tools, but now with our tool set, it gives you a straight path to software defining hardware. And that's part of why we developed it the way we did.
Thank you.
Also, it fits inside the RISC-V custom extensions because it introduces an instruction set architecture, which by definition in RISC-V, you have the common architecture, and then you have the extension instruction set architecture. So you can just add our instruction set into a RISC-V processor, and you can have a full hardware version of XVM working at scale.
Can you think of any advantage of using qubits in implementing these instructions or algorithms?
Yes. So we have worked the instruction set to be compatible with future quantum systems. You know, quantum hardware is not widely available, but the internal design, and that's why we picked X machines, because the letter X means it's a data-oriented machine. So if X is a vector, it's a vector machine. If X is a graph, it's a graph machine. So X machines are a very, very powerful foundation. But it has taken a lot of work to engineer for that mathematical foundation. So yes, X can also be qubits, so you have a qubit machine. Absolutely.
Thank you, John and Arun. Thank you so much. Sorry, I took too long.
Oh, thanks to everyone. And next week, I'd like everyone to put it on your calendar that next Wednesday we are going to have a very interesting talk by, let me see if I can get that up on the shared screen. So next week we have Øystein Lindebo, Instructional Ontology and Criteria of Identity. And then on the week after that, Kit Fine will be talking about truth maker semantics. So I hope all of you will be coming next week as we continue the second track of the summit. Bye, everyone.
Thank you so much.
Thank you.
Many thanks for John and Arun to come today, and great start of track 2. Thank you.
Yeah, great start to track 2.